For a pathogen to enter the body, it must penetrate the physical, chemical, and biological barriers in the skin and mucous membranes. Once the pathogen enters the tissues or blood, it encounters macrophages that carry out phagocytosis and natural killer cells that execute cytolysis. This initial encounter can trigger the production of chemicals that promote fever, inflammation, and more phagocytosis and cytolysis. An infection can hold out against nonspecific mechanisms and even overwhelm this initial resistance. Meanwhile, immune cells are being exposed to the antigens, initiating a specific response to the invader. Activated B lymphocytes produce antibodies, and activated T lymphocytes secrete chemicals to lyse or burst the infected cell. In addition, activated complement proteins enhance phagocytosis, lysis of cells, and inflammation. The processes of initial specific resistance result in an increase of the number of available antigens and trigger the proliferation of B and T cells. The number of antibodies increases exponentially. After a week or so, the specific responses effectively destroy the infecting microbe. Specific resistance remembers how to fight antigens that have triggered the immune response in the past. This is known as immunological memory, and for particular antigens can last for decades. Prior to the first exposure to an antigen, levels of antibodies and lymphocytes are low. While immune cells fight the first exposure, long-lasting antibodies and long-lived lymphocytes, known as memory B and T cells, are produced. The high number of memory cells produces a faster and more effective response to subsequent exposures to the same antigen. Immunological memory is the basis for immunization vaccinations, in which a small, measured exposure to specific antigens enables a secondary response against future exposures to the same antigen.